Okay, this is the 3.5 video to go through some of the extra examples that we skipped over in class, starting with these on even and odd functions. Remember that to know that something is an even function, you're looking for y-axis symmetry, and if something is odd, you're looking for origin symmetry. What that translates into is that if you're even, f of negative x will equal f of just regular x, and if you're odd, f of negative x will equal the opposite of f of x. So when we do the test, essentially we have to just change all of our x's to negatives. Now in this case, if you put in negative x, on the other side, it's just a 12. There is no x over here. So f of negative x does equal the original function. So this function is definitely even. If you try to do the odd test, you do the same thing that you did for even, but you try one extra twist. You try to pull a -1 out. If you pull a -1 out of a positive 12, it turns the inside back into a negative, because negative times negative would be positive, and that does not equal the negative of f of x. Because to be negative of f of x, you'd have to have a -1 out front and a positive 12 inside, because that was what the original function was inside. So this one is not odd. Okay, we have a couple more. This one is a quadratic. So we're trying to test it for even and odd. First, we'll do the even test. You plug in negative x everywhere you have an x. We then work this out. Okay, so negative times negative would be positive, so this would still be 3, but it would be positive x squared. Negative times negative is positive. And we bring down the +1. That does not equal the original function. So this one is not even. We'll do the odd test. You put in a negative x, and you do the same thing you just did for the even test, so you plug it in everywhere. You work out the signs. So this would just be exactly what we just wrote. The last step is you try to pull out a -1. That would change this all different signs. So this is also not a -1 times f of x. So that is not true. So not odd. In this case, you would put it is neither odd or even. Okay, so let's look at E, for the even test. We plug in negative x. That is going to be a negative x down there in that denominator. The negative is kind of hard to see. Let me rewrite that. There we go. Okay, so we cube that. That would stay negative then. And negative times negative would be positive 1 over x. So this is not the original function. So we are not even. When we test for odd, we do the same steps. Remember, this is just testing for symmetry. That's all we're really doing. We get a negative x cubed again and a +1 over x, but in the odd chance we try to pull out a -1. That would change that back to x cubed and -1 over x, and this guy right here is your original function times a -1. So we are odd. Okay, that's how you do the test for odd and even. I'm going to be skipping through a bunch of notes right now. I'm going to do a few of the graphs of transformations of functions that we skipped over in class just because of time. I don't remember which one of these we actually skipped over, so I'm just going to do this last little group again. If I already did them, just skip over it on the video. This is 2x cubed, so that's 2 times an x cubed. That means that we have a number out front that is not part of the piece being cubed. So this is going to be a stretch or a compression in the y direction. And when you're outside, it's exactly what you think. So we're going to be doubling the y's, which I like to say is a stretch in the y direction, but it's really double the y's. Okay, so when we look at that, oops, does not want to stay. We need to look at the parent function, x cubed. Remember, had the original shape like this with -1, -1, 0, 0, and 1, 1 being key points. Essentially, we're taking those same 3 points and we're just doubling the y's. So y times 2, essentially. So this becomes y is 1 is x is still 1, and 1 times 2 is 2. 0 would still be 0. You times this by 2, so that's still 0. Negative 1's not changing, but negative 1 times 2 is negative 2. So 1, 2, sorry, wrong side. 1, it didn't erase it. Erase. It's still not erasing. Okay, just ignore that point. 1, 2, 0, 0, and 1, negative 1, negative 2, sorry. And then this still has the general shape, just a little bit thinner than the one we originally have. Okay, if we put a 1/4, this is something out front. If you have a number out front that is a fraction, like between 0 and 1, this is actually called a compression in the y direction. Which means we take 1/4 of y. So again, this is a different parent this time. This is a parabola centered at 0, 0 normally with 1, 1, and negative 1, positive 1, because when you square it, it would be positive. Those are our 3 key points. We're going to be cutting all of the y's in a fourth, so times the y's by a fourth. So that's what we're doing. So this would be negative 1, 1/4, 0, 0, and 1, 1/4. 1, negative 1, 1/4 is right there, 0, 0, 1, 1/4. Notice this, oh, that's a little bit too extreme, but this is a wider parabola than what we had before. I went a little too wide on that side. Okay, if your number is inside your parentheses, so now this is the same guy I did a minute ago, but now the 2 is inside and being cubed. When it happens inside, it affects x, and it's always opposite to x of what you see. So instead of times 2, this would be a half of x, and that would be considered a compression in the x direction. So this would be, let's think about that x cubed guy again. He was negative 1, negative 1, 0, 0, and 1, 1. This time our x is going to be cut in half. So this would be negative 1/2, negative 1, because the y is not changing. 0 cut in half is still 0, and 1/2, 1. So negative 1/2, negative 1, 0, 0, positive 1/2, positive 1. So notice this is a very skinny, but it's compressed on the x-axis, so it's been squished in from both sides. And obviously it would be better if my grid was a little bit bigger. We did J in class. I'm going to make sure we talk about K. K has 2 different transformations. If you have a plus or minus something inside your function parent, which is being squared, that means you either move right or left, and it's always opposite to what you think. So this would be to the right 3. You can also think of that as adding 3 to your x value. And the outside number being added or subtracted is up or down, so it's always exactly what you see. So it's up 1, which means we plus 1 to our y values. This is an x squared essential case, so that means we're parenting a parabola. So this is negative 1, 1. And remember, these parent functions are at the end of these notes. You do need to study them. So if we move this right 3 and up 1, essentially I'm just going to move it point by point. So 0, 0 would go right 1, 2, 3, up 1. So that's my new vertex. My point negative 1, positive 1 would go right 1, 2, 3, up 1. And positive 1 would go right 1, 2, 3, up 1. So notice this parabola has just been moved piece by piece over. We did L in class, I believe, so let's do M. M has two things going on. We have a vertical shift, and we also have, since this is outside and not being cubed, because the cube is only applying to the x, this would be a compression in the y direction, because anything that's outside of the function affects y. So think about x cubed again. That's this shape. -1, -1, 0, 0, 1, 1. We're going to be taking half of the y and then subtract 2 from y. Because remember, anything outside of x cubed is happening to y. So let's think about this. I'm going to do it in steps because I wanted you to see how to do this point by point if you don't want to try to visualize it on the graph. So in this step, I'm going to take half of all my y's. So this would turn into 1, 1/2. This guy would turn into 0, 0. And this guy would turn into -1, -1/2. The next step I'm going to do is I'm going to subtract 2 from y. So that would make this 1, -1.5. Did not want to write it the way I wanted it to. So -1.5. This next guy would be 0, -2, because subtracting 2 from 0 actually does something. And this one would be -1 and then -2.5. So +1, -1.5, which would be right here. 0, -2, and -1, -2.5. So notice I get a compressed, or actually compressed in the y direction, squished, and it would also have the shifting down too. Okay, so the only other one left in this section is the second piecewise function. So just to remind you how to do a piecewise function, you do a table of values essentially for each part. These are each different functions defined on different domains. This tells you how to set up your domains. This says less than or equal to -2. So -2 and then things that are smaller. You do need to note if it's an open or closed point on that endpoint, and since there's an equal to, it is closed. For the middle, we move all the way from -2 up to 1, and you do include the endpoints in terms of your table, but in terms of actual dots that you put on the graph, they're both open. But you do have to have the endpoints even though they're open, just so you know where the graph is going to end. And then this last one is bigger than or equal to 1, and it is closed because of the equal to sign. So then we plug these in. So -2 minus 3 would be -5. -3 minus 3 would be -6. -4 minus 3 would be -7. This one you have to be careful. This is -2 squared. So you actually square it and then times it by the negative outside. So that makes this guy -4. -1 squared would be 1, but then you have a negative outside. 0 squared is 0, and you can't change the sign of 0. 1 squared would be 1, but we have the negative outside. This would be -1 plus 4 because of the negative that was there, so that would be 3. -2 plus 4 would be 2, and -3 plus 4 would be 1. So now we just have to graph these, and remember that these two are only bounded in one direction, so the graph will continue in forever in one direction with an arrow on the end. So for this first one, we have a closed circle at -2, -5. So that's a closed circle. It does not want to graph these closed circles. And then we need some other points plotted. So -3, -6, and -4, -7. And this keeps going back to -infinity forever. So you notice you get a line with a closed circle as its endpoint. For the middle one, we have -2, -4, and that is open. It does not want to graph these. And then we have -1, -1, 0, 0, 1, -1, or 1, -1, and that one's also open. So when we graph this, get part of a parabola, and then the last piece is, that's supposed to be open, is 1, 3, which is closed. Does not want to close it in. And then 2, 2, and 3, 1, and it goes forever in the positive direction towards positive infinity. So that is my piecewise function. And that is the end of this video.